we will discuss the model calculation of performance and heat balance test on a four-stroke single-cylinder diesel engine by mechanical loading. After completing the experiment, we have to do the calculation for the performance test as well as heat balance sheet to calculate the heat balance sheet on a four-stroke diesel engine by different loadings. If you are confident on a single any one of the loading model calculation, definitely it will be easy for us to calculate the remaining experiments. So based on this, we will move on to the observation first. Here, the specific gravity of fuel. Specific gravity of fuel. The fuel is diesel. The specific gravity of fuel is 0.83. Then calorific value of fuel, we can take the maximum value. It is 45625 kilojoule per kilogram. Then brake power. Brake power, you have to check the specification of the engine. In the name board itself, it clearly brake power is mentioned. If it is 5 HP or if it is 5 HP, 1 HP is equal to 746 watts. You can convert 5 HP in terms of kilowatt. It is 3.75 kilowatt. Then we have to calculate the cylinder area. Cylinder area depends on pi d square by 4. Here d is nothing but the bore diameter. The bore diameter, it is 80 mm. We have to substitute in terms of meter. 80 into 10 power minus 3. Then calculate the maximum load that can be applied to the engine in terms of brake power in kilowatt. We know that it is 3.75, and then n in rpm is the n is the speed. It is the constant speed engine, so that's why we are fixing it as 1500 rpm. Then cp is the circumference of the brake drum. Circumference of the brake drum in terms of a centimeter we measured, it is 94 centimeter. Here we convert that into meter as 0.94 meter. Then finally we obtain the maximum load as 16.26 kg. So that is the maximum load we can apply it on that particular four-stroke single cylinder diesel engine by mechanical loading. Next, we will check performance test tabulation. Whatever the reading, we can take it from the experiment. Here the applied load in terms of kgs, we can divide into four divisions. First one is no load. No load, there is no load. Without applying any load on the engine, we are going to run the engine. So load on the engine is 0 kg. Then 25 percentage of 16 kg. 25 percentage of 16 kg is 4. Then 50 percentage of 16 maximum load 16 kg is 8. Likewise, we can do the calculation for 75%, it is 12, 100% it is 60. And now we have to run the engine. First of all, you can check a few things like whether the fuel tank is filled with fuel and whether the cooling water motor is switched on, water is getting flowing into the engine for cooling purpose. And with these things, after checking these essential things, we can start the engine. And for no load condition, you can check what is the fuel consumption for 10 cc in the 10 cubic centimeter in the tube. And use the stopwatch and measure the time twice. For after that we can get an average. Okay. And for model calculation, always don't prefer this no load, because most of the performance parameters will be zero for us. So instead of doing the model calculation for no load, we can go for either 25%, 50%, 75 and 100%. It will give values for all the parameters. So in this model calculation, in this video I have chosen the model calculation percentage for 25% 4 kg. So here also for our reference, I have added a few readings. 26 is the average time taken for fuel consumption. Here one more thing, based on your requirement, you can measure the fuel consumption. It may be for 10 cc or 5 cc. So most of the times we will use 10 cc fuel consumption. In case if you used 5 cc 5 cc for 5 cc of fuel consumption, you may measure the time taken. So based on your uh, experiment, you can choose the fuel consumption time taken. Okay, if it is 10 cc, time will be more. If it is 5 cc, time may be less. Okay, so this is exclusively we calculated. I used those readings for 5 cc instead of 10 cc of fuel consumption, so that I have to use this 5 cc for model calculation. 25% low, that is what we are going to do. Then fuel consumption fc in kilogram per second, and for this kilogram per second, we know what is the specific gravity of fuel. Then volume of fuel consumed in cc. What is specific gravity? It is 0.83 as per the observation of specific gravity of diesel. Volume of fuel consumed in cc, I told in the observation for that particular reading we used 5 cc, that's why it is 5. And T average for no load and 25% load 4 kg is 26. After substituting all these values, we can get what is the fuel consumption in terms of kilogram per second. Next, we have to calculate the same fuel consumption in terms of kilogram per hour. It will be useful for us in the upcoming parameter calculations. Just seconds into hour. So 1 by 3600 has to be multiplied by 3600, being seconds in the denominator. So it has been converted to kilogram per hour. Next one is fuel power in kilowatt. So fuel power, whenever we say power, that the unit is in terms of watts. For that we can multiply the calorific value with fuel consumption. What is the calorific value? 45625. After multiplying, we will get an answer. Then finally, it is a brake power. Why? What is brake power? First of all, the brake power is the power which obtained on the crankshaft. That is our output of the engine from the combustion of the air fuel mixture. So CB, we know that circumference of the brake drum in terms of meter it is 0.94, and in RPM is 1500. 9.81 is the general acceleration due to gravity standard value. L in kg is, for us it is 4 kg. In case if you are performing the model calculation, for you are doing the model calculation for 50% or 75%, here your load may vary. Okay, next find out what is the answer for this brake power. Next parameter, it is specific fuel consumption per kilowatt hour. What is the fuel consumed in terms of kg? I have to calculate. So fc in kilogram per hour, it is calculated in the step number 1. It is calculated in the step number 1, and the brake power is calculated in step number 3. Use these two values and find what is specific fuel consumption in kilogram per kilowatt hour. So it is also easy. So all the data are known. We can easily calculate kilogram per kilowatt hour specific fuel consumption. Next step, we have to calculate what is the friction power. For calculating the friction power, there are different 4 methods are available. One is like this Williamson line method, and next one is we can use the formula of indicated power. Uh, then what is, we can use the formula of indicated power is equal to brake power plus friction power, because indicated power is the power which is produced during the combustion process. Input, which is the heat energy, is the input which driving the crankshaft. The crankshaft, whatever the power we are obtained in the crankshaft, it is brake power, and frictional power is the loss. So whatever the power we are producing combustion combustion process in terms of heat energy, has to be some power utilized as useful work, that is the crankshaft power. Crankshaft, whatever the work we obtain from the crankshaft, is the brake power, and losses we can say it as a frictional power. Second method. Third method is the retardation test. Using retardation test also we can calculate friction power. Final one is Morse test. These are the 4 methods available for calculating the friction power in the internal combustion engine, irrespective of any loading: mechanical, electrical, eddy current, and hydraulic loading. Here you can check in the x-axis, it is brake power. You can have a negative side x as well as positive side x in terms of kilowatt. Then fuel flow rate in terms of kilogram per hour. Make sure that here you have to use kilogram per hour, not kilogram per second, fc. And here we know that the constant engine speed 1500 rpm. And don't follow as this as a scale like this. We will check what our range of values. For us, the brake power it is 0.92 kilowatt, fuel flow rate is 0.5724. In this case, what we can do, we can take like point 0.4, point 0.8, 1.2, 1.6, 1.2.0 like that. Similarly, the same scale has to be used on the negative side, zero point 0.4, 0.8, 1.2 like that. In case of y-axis, what we can do is we can go for being 0.5724. You can check the consecutive readings, check the reading values of fuel consumption at 50% load, 75% and 100%. After checking this, you can check the range of values. It may be like 0.25, 0.5, 0.75 or 0.51, 1.5 like that. After completing the graph using this x and y values like brake power and fuel consumption, then you can extend a graph through that point. It will meet on this point A, any point on the negative side of x-axis. That is the exact value of your friction power. That is your exact value of your friction power. Here if you look at this exact scale, it may be uh, 4 plus, okay, 4 plus. But in our case, actual calculation part, you can check your calculation reading values. Based on your reading values, you can take a scale here. Okay, then I'm going to assume for this it may be being brake power as 0.92 kilowatt and fuel consumption 0.724 kilogram per hour. Mostly what is the maximum brake power of our engine? It is 3.75 kilowatt. 3.75 kilowatt. So remaining the friction power may be like in the 3.75 kilowatt, our friction power may be around 1.5. So for that, what I can do is I assumed the value as 1.2 kilowatt. Based on our reading, I assumed 1.2 kilowatt. You can draw a graph on you for your reading and obtain from the graph whatever the values it is touching on the negative x-axis. Okay, so based on that, you can do the remaining calculation. Indicated power, we know that it is the input power. It is the input power which is generated during the combustion process, nothing but is equal to brake power plus friction power. We know that brake power already calculated as 0.92. Now it is 1.2 kilowatt. You can add both the values and tell value as 1.2 kilowatt. After adding this, it is not 1.2, it is 2.12. Here it's a mistake. It is 2.12 kilowatt. Then find what is mechanical efficiency. This mechanical efficiency, brake power by indicator power. In general, efficiency can be defined as output by input. Here the output is the crankshaft power, brake power. Input power during the combustion. During the combustion, whatever the heat energy we produced is the indicator power, input power. So output by input is brake power by indicator power. So tell me what is the efficiency of this particular engine? It is 43%. Then similarly we have to calculate brake thermal efficiency. Brake thermal efficiency is whatever the fuel power consumed, whatever the fuel power is produced with the help of fuel power. In that fuel power, how much percentage we produced as output? Nothing but our brake power. So brake power with respect to fuel power, it is 12%. If you calculate with respect to indicated power, if you calculate indicated power percentage with respect to fuel power, it will be more because it is being an input, it will be more than the output. So here the percentage will be on the higher side. Then last one is a mean effective pressure. While during combustion or during the generally we will define what is mean effective pressure. During combustion, there will be a pressure difference inside the cylinder. If you check at the top of the air fuel mixture inside the cylinder, the pressure may be somehow lesser than the bottommost air fuel mixture. So you will feel the pressure differences between inside the cylinder For that, what we are going to do is we are going to take the average of mean. That's why we are saying the mean effective pressure. Okay, if you calculate with respect to brake power, it is brake mean effective pressure. If you calculate with respect to indicated power, it is indicated mean effective pressure. Brake power in terms of kilowatt, we know that it is 0.92 kilowatt. And cylinder area in meter square. What is cylinder area? Pi by 4 d square. So d is the cylinder bore diameter. It is 80 mm, 80 into 10 power minus 3 meter. That is the value of d. Then stroke in meter. It is 110 mm. Stroke length. Stroke length of the engine. What is the stroke length? The piston which is covering the distance inside the cylinder from TDC to BDC. This is the stroke length. Then speed N1 in RPM. In case of 4-stroke engine, we have to take it as N by 2. Why? This N by 2 is in 2 revolution only we can produce one indicated power or brake power, because in 2 revolution we will have one combustion process. In case of 2-stroke engine, in a single revolution I can produce a one power stroke or power process, combustion process. Okay, so that is the reason behind n by 2 for 4-stroke engine, n for 2-stroke engine. So 1500 being 4-stroke engine, in our case it has to be 1500 by 2. Next one is bar. You can calculate the brake mean effective pressure in terms of bar. That is the reason here we are using 100. Okay. Then indicated mean effective pressure, we know that instead of brake power, we are going to use this indicated power value. This is not 1.2. 1.2 plus 0.92 is 2.12 kilowatt here. Okay, there is a mistake. It is 2.12 kilowatt. Use that indicated power as uh, substitute here and find what is indicated mean effective pressure. It will be more than the which one? Brake mean effective pressure. Next. Then we have to calculate what is the torque. Torque produced at the torque produced by the engine. The force in terms of Newton, then brake drum effective radius in meter. The force in terms of Newton. Here it is the load kg. Load in terms of kg multiplied by 9.81 will give us Newton. The load for us, it is 4 kg. And radius, this radius is nothing but cb in terms of meter, circumference of the brake drum. Wherever you are calculating the torque or output regarding brake power, so we have to use the circumference of the brake drum. Here it is 0.94 meter. Use this all the known values, substitute and find what is the torque in terms of Newton meter. This is all about the performance test calculations, model calculation, performance parameters. After calculating all these performance parameters, you can tabulate in this result tabulation. If you check most of the cases, fuel consumption. What about fuel consumption? If the load is getting keep on increasing, our fuel consumption will also increase. If the fuel consumption is increasing, what about our brake power? Brake power will also increase. Similarly, indicated power, mechanical efficiency, fuel power, brake thermal efficiency, indicator thermal efficiency, including torque. If the load is more, I have to produce more torque to run the engine. So all the readings will increase except this specific fuel consumption, because you may ask specific fuel consumption per kilowatt hour. What is the fuel consumed? Per fuel consumed per kilowatt hour. Keep on increasing the load, the fuel consumption per kilowatt hour power production will be decreased compared to all other parameters. This is one. You may after calculation you may check whether it is increasing or decreasing. Each and every numerical value has a concept behind it. You can correlate your concept with these calculated values in the result tabulation. So that is why this is and one more thing here, FC you have to tabulate by means of kilogram per hour. Why? In billions graphical method for finding frictional power, we have to use kilogram per hour, not kilogram per second. So you can use kilogram per hour values for tabulation here. Okay. Next one is a graph. First graph already we completed. With the help of that first graph, Williamson graph method, one graphical method only, we found the friction power. Next, remaining thing is you can take brake power on the x-axis. In the x-axis, it is a brake power. You will have three, four variables in the which one? Four, actually five. You can check here. Y1 it is variation of specific fuel consumption, and you may combine make it as two graphs. For efficiency, one separate graph, remaining you may follow for another one graph. Variation of specific fuel consumption, brake mean effective pressure, indicated mean effective pressure, torque. It may be drawn on a single graph with three y-axis, and draw a separate graph for these three efficiencies: mechanical efficiency, brake thermal efficiency, indicator thermal efficiency. Brake thermal efficiency has the highest value compared to brake and the indicator. So compared to brake, indicator thermal efficiency has more value because of indicated power is the input of the heat engine, IC engine, and brake thermal efficiency is the based on the indicated power produced during the combustion process only. We can obtain some useful work from the crankshaft. Okay. With this, we will move on to heat balance test or heat balance sheet. What is the need of finding this heat balance sheet? We said the mechanical efficiency is only 40%, and even if you check the thermal efficiency of brake thermal, indicator thermal efficiency is like around 30% and 20%. So it is, so we have to know where this heat energy is getting lost uh, before converting into useful work. Okay, where it is lost, like whether it is carried away by cooling water or by means of friction or by means of simply it is exposed to the atmosphere through exhaust. This is the need of finding the heat balance state. Why we are saying heat balance? The input of the engine is the combustion. During combustion we are producing some amount of heat, but this heat is not exactly converted into work. That is what we studied in Kelvin Planck statement of engineering thermodynamics. So it is not possible for us to construct a machine to convert 100% heat into 100% useful work. Here also there is a losses. We'll check what are the observation essential for this heat balance test. Some of the observations already we discussed in the performance test itself. Here the room temperature you may measured at the beginning of the experiment. Here I assumed as like 35, uh, not 35, it is 32 degrees Celsius, 273 plus 32 is 305. Then specific heat of water it is 4.186, and specific heat of gas, nothing but our air, 1.005 kilojoule per kilogram Kelvin. Then specific gravity of fuel we know that it is 0.83. Coefficient of discharge is 0.62. Calorific value of fuel we know that 45625. Then brake power 265. Brake power it is 5 HP, 3.75 kilowatt. So these are all the things we well known for us. Here the one more different parameter is area of orifice. Area of orifice. So again pi d square by 4. The area of orifice is nothing but the where our air intake goes inside the cylinder. And in this orifice diameter it is 14 mm, 14 into 10 power minus 3 meter. You can calculate this area of orifice for further calculations, upcoming calculations of heat balance. The maximum load we know that it is 16.26 kg. We are going to make it as 16 kg as maximum load. Here we will do the same model calculation for 25% load of 4 kg. For this time consumption for 10 cc of fuel consumption or 5 cc of fuel consumption, we accounted for 5 cc of fuel consumption. That's why it is 25. If you are used for 10 cc, it may be more than 50. Okay, more than 50 seconds. Cooling water temperature, inlet cooling water temperature and outlet cooling water temperature. Definitely, outlet cooling water temperature will keep on increase by increasing the load, because the engine heat is keep on increasing while we are adding the load, and it will be more than the inlet temperature of water. Then this is not liter per minute. If you check the rotometer of which is connected for measuring the flow rate of water, the unit in the rotometer is liter per hour. Okay, liter per hour. By the floating needle, you can check what is the mass flow rate of cooling water. For here, for my calculation, I took it for as 130. Convert this liter per hour into kilogram per second divided by 3600 seconds into hour. Then exhaust gas temperature. Using the temperature indicator, you can measure what is the exhaust gas temperature. Manometer readings H1 H2 in terms of centimeters. That's why here itself commonly given as 10.2 meter, 10 power minus 2 meter, and find what is the difference. So with these 25% of maximum load 4 kg, we will do the calculation. Next is we will check model clash calculation 25% load. First three is similar to the performance test. Fuel consumption in terms of kg per second, then fuel consumption in kg per hour. Next we can calculate what is fuel power and multiply by cv, calorific value, 45625. Next one is brake power again the same value, 0.92 kilowatt. So first three calculations is similar to the performance test. We will next we can check what all the else we can calculate in this heat balancing. We know that heat is carried away by some part of the heat is carried away by cooling water. Generally it is for Q, it is mc del T. Here it is of cooling water, mcw is nothing but mass flow rate of cooling water in terms of kg per second. Cpw is specific heat of water in kg per kilogram Kelvin. T0 minus Ta is the cooling water outlet temperature minus cooling water inlet temperature. It has to be substituted in Kelvin. Okay, now after substituting all these values, because these all mass flow rate can be taken it from the tabulation, and Cp of water is standard value, that is what we return in the observation. All the values are known to us. With that you can calculate what is heat carried away by the cooling water. Next one is heat carried away by exhaust gas. Again the same formula, mc del T, mass of exhaust gas in terms of kg per second, Cp of gas, specific heat of gas in kilojoule per kilogram Kelvin. Then del T is the temperature of exhaust gas minus temperature of room temperature. So room temperature, in the beginning of experiment we measured what is the room temperature using the temperature indicators. So here mass of exhaust gas, the exhaust will have both the fuel as well as air. After combustion of air fuel mixture, we are getting the exhaust, so we have to add both the mass of air and mass of fuel. So you can check here, the mass flow rate of exhaust gas is mass flow rate of air plus mass flow rate of fuel. And mass flow rate of fuel, fc in kg per second already we calculated. We did the calculation part in the performance test itself, so it is known data for us. Here the unknown is mass flow rate of air. Mass flow rate of air we can calculate from Q is equal to, already we know that mass by density, or mass equal to volume flow rate of air, volume flow rate of air in terms of meter cube per second into density of air. Here both the data are unknown. QA as well as density of air is both are unknown. For that what we can do, the general formula is we know that atmospheric pressure divided by gas constant into room temperature. Atmospheric pressure, what is the atmospheric pressure in terms of Newton per meter square? It is 1.0132 into 10 power 5 bar, 132 135. Gas constant, it is joule per kg Kelvin, it is 287. If it is kilojoule per kilogram Kelvin, it is 0.287. The unit is joule per kilogram Kelvin. Next, room temperature. We know that what is the room temperature. We took it from the temperature indicator in the beginning of experiment. So density of air is calculated in this step, but still the unknown is which one? Uh, Volume flow rate. For volume flow rate, formula is CD into area of orifice divided by velocity of air, because area of orifice will give us meter square and this is meter per second. Finally I will get meter cube per second. Area of orifice we calculated in the observation itself, pi by 4 d square, pi d square by 4, where orifice it is 14 mm. Okay, and unknown again it is velocity of air. So coefficient of discharge is 0.62, area of orifice we can refer observation in the heat balance sheet beginning of the experiment. Then velocity of air we have to calculate it as root of 2gha in terms of meter. H is the head of air in meter, g is 9.81. Here again unknown is ha. So first we have to calculate the height of the air column. Height of the air column using density of water with manometer reading, because we used in the manometer the fluid as density. With that we can calculate HA rho A is equal to rho W HW. Here the unknown is HA. Density of water is 1000 kilogram per meter cube. Manometer reading, I think we identified something around 10.9. So in terms of centimeter, here I have to substitute in terms of meter. That's why it is 0.109 meter. Then density of air. We know the density of air. From the beginning itself, we calculated in the previous step. We calculated the density of air. Here check, this is the density of air rho A we calculated in the previous steps. So with this all the data are known, we can easily calculate HA. If you know HA, substitute the HA in the velocity of air. Here velocity of air can be calculated. After finding out the velocity of air, go to volume flow rate. Here velocity of air we know now. With this area of orifice and coefficient of discharge also known data, I can complete QA. If I completed QA OA, I can complete what is the mass flow rate of air. Already we know mass flow rate of fuel. By adding both, finally we can achieve the mass flow rate of gas, exhaust gas. Now all the data are known for us. We can calculate what is the per kilowatt, or the what is the uh, quantity of heat carried away by the exhaust gas. Next one is we have to check what is the unaccounted loss. We know fuel power. Fuel power, by combustion we produced some power. In the few by calorific value of that we know what is the fuel power that can be produced. And finally what we got, some useful work output as brake power. Some heat has been carried away by cooling water. Some heat, part of the heat has been carried away by exhaust gas. So what about the remaining things? In case, say for an example, for me fuel power is 100 kilowatt. So if I add all these things, I should have get again 100. In case if I doesn't get the didn't get this 100 value, which means there is some more losses are there. It's unaccounted losses. So after calculating all these values, we can find what is unaccounted loss. Now we are going to calculate what is the percentage heat equivalent of brake power. What is the percentage of brake power we produced with respect to the fuel power? Likewise, we can calculate the percentages for brake power, all the parameters: brake power, cooling water, heat carried away by cooling water, heat carried away by exhaust gas, then accounted loss, unaccounted loss. For all these four parameters, we can calculate the percentage with respect to the input fuel power. Finally, do the tabulation heat balance sheet. So as we said, heat input is fuel power. Heat input is fuel power that has been considered as 100%. This 100% is splitted into some percentages for heat carried away, heat equivalent of brake power, nothing but the useful work produced in the crankshaft, and some heat lost is heat carried away by cooling water. Some heat has been lost to the through the cooling water. Then heat losses to the exhaust gas. And finally some of the heat is lost. We don't know where it is lost at. That's why it is unaccounted loss. By adding all these values, we should have get again this 100%. So QBP, QCW percentage, QEG percentage, Q unaccounted percentage. If you add all these values, once again you have to get this same 100 percentage. Then only your heat balance sheet is right. That's why it is heat balance sheet. Okay, you have to balance the whatever the heat you given it as an input has to be balanced where it is lost, how much percentage you converted as useful work, and what about the remaining percentage of heat energy where it is lost, like heat carried away by cooling water, heat carried away by exhaust gas, and some heat is for unaccounted losses. So with this result tabulation, we obtain the heat balance sheet for all the loads. Like for one is for 0 percentage no load, then you can check it for 25%, 50%, then 75 and 100%. So with this I can know what is the heat balance sheet. Now I have to draw the heat balance sheet. Now you can check the percentage of load in 5 divisions. 5 divisions, either it may be like x-axis, this is the percentage of load, maybe 0, 5, 10, 15, 20, 25, like that you can divide. Because why we have drawn here it is 0, 25, 50, 75, 100. That is how we splitted our maximum load as 25%, 50%, 75 and 100%. If you draw with this x-axis scale, it may be tough for us. The graph will be very minimum. So instead of 0 and 25 divisions, we may for at least we will go for 10 divisions: 0, 10, 20, 30, 40, 50. For y-axis, the percentage of values where it is lost. What is the percentage of heat carried away by brake power? So we have those values in the heat balance sheet. Percentage of heat equivalent to the brake power for all the loads. So first you can use those percentages. First draw the graph of brake power. This blue shows the brake power. For next graph, what you have to do is add the brake power and the indicated power. Sorry, brake power and the cooling water. For next graph, what you have to do, add brake power heat loss percentage and cooling water heat loss percentage. Okay, so see here the brake power plus cooling water. If you take this red alone, it is cooling water. Red alone, it is cooling water. If you take this line above the red, you are having a line. This is the combination of both brake power and cooling water. Next thing, you have to add brake power, cooling water heat loss, and heat carried away by exhaust gas. Add both these values, draw the third line. This is the third line. Above the green graph, you are having a third line. For this, you have to add brake power, cooling water percentage, heat carried away by cooling water percentage, and heat carried away by or heat lost to the exhaust gas. And after completing these three lines, you differentiate by means of different markings. You may do hatchings, and you can give some different notations for identifications. Whatever the remaining percentage is obtained above these three things is the unaccounted loss. You can check most part of the heat energy is lost by means of unaccounted. It may be like frictional loss or whatever it may be. So with this, once again I insist, go for this graph as clear as possible. Here it is brake power. After that you can add brake power plus cooling water for the second line. For third line it is brake power plus cooling water plus exhaust gas, and finally the remaining portion has to be shown it as unaccounted loss. So far end this 100%. Okay, 100% we have to show in the heat balance sheet. Okay, so this is how we have to do the calculations for remaining experiments, like performance and heat balance test of a four stroke single cylinder diesel engine by mechanical loading. We discussed in this session right now. The similar, more or less similar calculations for hydraulic eddy current and which one electrical loading. Only thing the input will vary, like in terms of amps. you may calculate it for electrical and AD. Hydraulic also again in terms of kgs. Only thing for calculating brake power, for sorry torque in the performance test, here we used force into brake drum radius. But in case of those three loadings, we will use brake power is equal to 2 pi nt by 60. Here the brake power already we calculated in step number 3. Torque is the unknown data, so we can calculate, use that formula for torque to find the torque. If you find this video as useful, you can share with your friends. Also subscribe this channel for other videos. If you have any doubts or any clarifications, if you need in this particular calculation, you can ask through comment box. And also, if you like the video, if you feel it is helpful for you, you can like this